All right. Oh, my camera was just working a second ago. All right. I hope everyone is doing well today. Let me know any questions, needs, comments, concerns, etc. about literally anything that you have before we get started. As a quick review, this week we have begun our discussion of magnets and magnetic fields. So this will be labeled chapter 1920 because we're kind of picking and choosing selective things out of the textbook. I do recommend looking over the homework for this as we go through the week. Yesterday we introduced the concept of magnetic fields and the interesting fact that magnetic fields can exert magnetic force on electrically charged particles, and the odd kind of 3D nature of how those things interact. We'll review that today and start using the formula that we looked at yesterday. This week we'll continue with that. We are scheduled for a lab this week, but stay tuned. I'm still finalizing exactly what we're doing this week, so I will let you know via email either today or tomorrow exactly what the plans are for that. Main thing to be aware of is that this will be the last chapter before test 2. So, like how test 1 was, test 2 will be opened up towards the back half of next week. You'll have from it opens through the weekend to do it, and then we'll spend a week or so after that talking about waves and getting ready for the final. That should all be review, and I apparently just like to repeat myself, or I feel the need to repeat myself. So, let me know if there's anything you need before we get started as I get the notes set up for today. All right. Sure that's recording. So, various objects and things in the known universe create magnetic fields. These fields are similar but distinct from electric fields. For example, Earth has a magnetic field, which is important because Earth's magnetic field is able to protect us from excess radiation and debris from outer space. If it was an electric field, it probably wouldn't be quite as good at doing that particular job. Let me go to a different slot. Come on. Well, that's weird. It's not letting me erase anything. Well, okay. Sorry about that. The formula that we looked at for describing the relationship between magnetic fields and the force that the magnetic field exerts on an electrically charged particle is as currently shown on the screen. Force from the magnetic field is equal to the charge of the particle moving through it times its velocity through the field times the magnitude of the field itself. As a reminder, B represents the strength of a magnetic field, kind of like how big capital E represents the strength of an electrical field, and the unit for magnetic field strength is Teslas. What this means is that as a charged particle moves through a magnetic field, the magnetic field will exert force upon it. We looked at a few examples of places where that happens, one of which is this apparatus currently pictured on screen, where an electron beam is being fired through a magnetic field, and as a result, the beam is under various forces, causing it to bend and change direction. But another very important place where this happens in nature is, again, Earth's magnetic field protecting Earth from radiation and space debris. The sun gives off lots of charged particles that are being fired towards Earth. Those charged particles will hit Earth's magnetic field. Because those particles would be moving through the magnetic field, there would then be a force on those charged particles, and that has the effect of deflecting them away from Earth, which keeps the surface of the planet from being constantly bombarded by all of that space dust, which is good. If Earth didn't have a magnetic field, and if we were being bombarded by all that space dust, Earth would look a lot more like Mercury, where the day side of the planet is basically on fire all the time, and the night side of the planet is a permanently frozen wasteland. So, Earth's magnetic field is a very good thing, besides the fact that it lets our compasses work. And as a side effect of this, when those charged particles are deflected, they give off energy that create the northern and southern lights. So, again, just keep this formula in mind because we're going to start applying it mathematically today and then looking at a few related concepts. The weirdest part of this formula is, again, the relationship between the direction of all the parts of it. Force equals charge strength times velocity times field. This version is kind of flipped, switched the V. No, it didn't. Never mind. Note that force and velocity and magnetic field are all vectors. They all have to point in a specific direction. The field lines point in a direction, velocity points in a direction, and force points in a direction. All of these vectors are designed such that they are all perpendicular to each other. And the only way for three different things to be perpendicular to each other is if they are in the three separate axes, x, y, and z. So as a result, we use the right-hand rule to try to demonstrate the relationship between velocity, magnetic field, and the resulting direction of force acting on the charged particle. For example, on this slide we looked at a few specific cases. These X's represent magnetic field lines pointing into the screen, kind of like the tail end of an arrow that you're looking at after it's gone through the paper. Magnetic field into the screen, the... Oh. Current field for... Well, shoot, I'm realizing that I might have got this backwards yesterday. Field into the board, current that way. The force would actually be upwards in that case. Whoops. Okay, so getting right-hand rules right for this takes a little bit of practice because it is very strange. Like, having to keep track of it in this way is not... It's possible to be something that you haven't really done before, and frankly, it's something that I, out of practice, can still make mistakes on. So... as a reminder for the right-hand rule, you hold your hand open, kind of like an L. Your fingertips point in the direction of current. Your palm points in the direction the magnetic field points, and as a result, your thumb will point in the direction that the force is in. So if you're following along with A again, field points into the screen, the velocity of the particles is to the right. I'm holding my hand correctly from my perspective. What you see on screen might be backwards. So the resulting force would point upwards. Main thing to note is that if the field and the velocity aren't perpendicular, then you won't get any force. For example, looking at C here, the velocity is parallel to the magnetic field lines. There would not be any force in that particular situation. So there's a few right-hand rules practice questions on the homework. Some of the homework questions for this chapter are just, here's the field, determine what direction the force on the particle would be. I do encourage you to start those up. There's no penalty for constantly just retrying them and redoing them, just to help get the practice in for how this method works. So, excuse me. Let's get a little practice using the math side of the formula then. An electron, whoops. An electron is traveling straight in the x direction at 30 meters per second when it finds that it has entered a magnetic field of strength 2 Tesla. Again, the capital T is short for Tesla. That's the strength of the magnetic field, pointing directly up in the positive y-axis. What is the resulting force on the electron, both its magnitude and its direction? So, using our new formula, force equals Q times V, specifically V perpendicular. Oh, come on. My computer keeps swapping between cursor and marker mode. V perpendicular to B. In this particular case, the velocity is pointing in the x-axis and the magnetic field is pointing in the y-axis. So these two things are perpendicular. There's nothing strange here. We can just multiply the two numbers we were given. We do need the charge of a electron. So charge of an electron is a constant. We have a table for that in chapter 15 notes. Negative 1.6 times 10 to the negative 19th. Next, we're going to multiply that by the velocity and then times the magnetic field. And that's going to be equal to the total amount of force that the field will exert on this particular particle. Negative 9.6 times 10 to the negative 18th newtons, which is not a lot of newtons, but an electron has a very small amount of mass. So this small amount of force on that even smaller mass would create a pretty noticeable effect. Next, we would use the right-hand rules to try to determine the direction that that force will point in. And I'm realizing in retrospect I might have made another mistake here. I apologize. We'll work it out together here now. Using right-hand rules to determine the direction of this force, the velocity points to the right, the magnetic field points in the positive y, and therefore, from, again, my perspective, I'll turn my hand around in a second, my thumb is pointing out of the page. I'll turn around now to try to match what your view sees. Make sure that this is showing up on camera. Current points in the x, magnetic field points in the positive y, therefore the force, my thumb, will point out of the page, sort of towards your face if you're looking at it. And that would be true if this was a proton, when I was writing this down, I forgot that this was an electron, and by virtue of it being an electron, it does always the opposite of what a proton would do in any given situation. So that one's on me. I apologize. It would actually be into the page. Your thumb would still say out of the page because right-hand rules are designed for protons. I do apologize for my inconsistencies on this one. Apparently, I haven't practiced my right-hand rules in a minute. So, again, this is meant to show the perpendicular nature of all three of these different variables. And we do now know what direction the force is going to point in. It's going to point into the page. We could call that the negative z direction. Now, that particular force is going to act on the electron and cause it to accelerate. Whenever a force acts on a mass, that creates acceleration. So the velocity of this particular electron is going to begin changing. As it's being pushed into the page, its velocity is going to start switching directions, and it's going to begin pointing into the page. But something weird kind of happens. As the electron begins changing its direction, that's going to change. That inherently changes the direction of its velocity. Changing the direction of its velocity is then also going to change the direction of the force that is acting on it. So, magnetic field still points up. Magnetic field still points up. That doesn't change, but the velocity, the direction your fingers point, is going to begin rotating. And as that rotates, the magnetic field still points up, but the force is going to constantly change direction along with that velocity. As a result, since the force is constantly changing direction, the velocity is also going to constantly keep changing direction. And the resulting pattern you get is a circular one. Has the potential to be a circular one. If you fire a charged particle into a magnetic field and everything lines up just the right way, you could hypothetically get a situation where the charged particle just continues spinning in place inside of that magnetic field. Given that the velocity and the force will always be perpendicular to one another, as long as they keep changing directions, you get a situation where the magnetic force kind of literally acts as a centripetal force. It's always pointing to the center of some orbital circle, and the velocity keeps changing directions to always point tangent to the circle as that force keeps changing direction. So you get this situation where the proton or electron starts undergoing circular motion if it's fired into a field at the correct angle. Now, you probably would not ever notice or think about this in your day-to-day life, admittedly, but there's at least one key place where this sort of thing does come up, and depending on what things you go on to study later in your careers, this may be more or less relevant. This is the technology that's used inside of, I forgot the term for a second there, mass spectrometers. Mass spectrometers and electron scanning microscopes are capable of utilizing this phenomenon to help identify what a certain particle likely is. Namely, what happens when you're using a mass spectrometer, which, if you're unfamiliar with the term, it's a machine that's designed to tell you what something is made of. You input a sample, it blasts a tiny piece of the sample off, usually just a few atoms, and it's able to identify those atoms. The way that it does that is the machine removes a few particles from the sample and gives them a velocity inside of a magnetic field. Now, if those particles are charged, and most subatomic particles are somewhat charged, velocity in a magnetic field is going to create some amount of force. So they're all going to begin spinning through that field. Now, inside the mass spectrometer, what ends up happening looks a lot like the picture to the left, more so than the picture to the right. Mass spectrometers don't have particles spinning in whole circles indefinitely. What they do is they fire the particle straight in so that it enters a field. As it enters the field, it's going to begin turning at a certain turning radius. And the amount to which it turns is going to depend on what this force is and the mass of the particular particle. Even if two charged particles have the same force acting on them, they might form different circles, because if they have different masses, they're going to accelerate at different rates. So the size of the semicircle that forms is going to depend on what the particular particle is made of, what its charge is, what its mass is. So a mass spectrometer fires particles into a magnetic field. They're going to begin turning as they're in the field, but the field is only shaped such that it'll form a semicircular radius. Again, you don't want, inside a mass spectrometer, you don't want it spinning forever. What they do is they have it enter the field, turn 180 degrees, and then exit the field. And then after it exits the field, it's going to travel in a straight line to strike a sensor. So the point of the field exists really to slingshot the particle back around onto a particular sensor plate. And since different particles will have different forces acting on them, and then they will accelerate to different degrees from those forces, every different type of particle, every different element, every different ion, every different isotope is going to have a different turning radius in this situation. And so as a result of having different turning radii, different elements, different isotopes, since they'll have different turning radii, are going to exit at different spots. They'll all end up traveling in a straight line, but they're all going to exit the field at different points. And so they're all going to strike the sensor in different places because they had different turning radii. And the purpose of the function of a mass spectrometer machine is that it can tell, it's coded to know if material strikes this part of the sensor, then that must be carbon. If material strikes this part of the sensor, that must be nitrogen or something. If something strikes here, then it might be iron. It's designed to know what something's made of based on where the particle strikes the sensor. And it's able to tell, like, if a certain percentage of the particles hit here, if a certain percentage hit here, it can figure out what compound something was made of based on where certain parts of it strike in certain ratios. So it's overall a very smartly designed machine, and it utilizes this principle. A lot of my students end up doing bio and chem work, and so at various points you might end up using a mass spectrometer or an electron scanning microscope, which can have similar technology built into it for the same purpose. So I'm hoping that this is useful information. If you encounter one of those machines in your studies, that's how it works. I find it very interesting. So, F equals QVB is the formula, the principle that causes this particular phenomenon. Now, your right-hand rules will still tell you the direction of the original force in relationship to the original field and the original velocity. But if the velocity starts changing, the force direction will also start changing, and you usually end up with some sort of a turning pattern as a result of that. the magnetic force in this situation acting as a centripetal force. Again, let me know any questions or issues you're having as we discuss these principles. There is an additional formula that some very smart people designed to figure out what that turning radius should be. I mentioned a second ago that the magnetic force in this formula, F equals QVB, acts as a centripetal force. And so someone took this formula and set it equal to the formula for centripetal force. And after doing that, they solved for turning radius after simplifying the formula. And so this new formula, R equals mv divided by qb, exists to tell you the turning radius of a particular particle in a magnetic field based on its mass, its velocity, its charge, and the strength of a field. And so this is the formula that those mass spectrometers utilize. It knows based on where it strikes the plate what its turning radius must have been, and from there it does some work to figure out what the particle was made of. So this is a new formula that can be used specifically for calculating that turning radius. For an example, here we have a particle currently moving in a helical pattern. In this specific case, we would have the constantly changing velocity vector in the zy plane, but this particular particle has some x velocity that is not being changed by the magnetic field, since the magnetic field points in the x-axis. So this is a three-dimensional picture. The particle was moving in both the x-axis and the y-axis at the same time. Since the magnetic field is in the x-axis, it's going to give a force in the a constantly changing force in the zy plane, causing the particle to begin moving circularly in the zy plane. But that x magnetic field is unable to stop the x component of the velocity. Since the field and the velocity are parallel, there's no interaction there. And that means that the particle can still move forward as it is rotating helically. It's kind of hard to see this in nature because you tend not to be able to see charged particles, but this pattern of motion is pretty common for charged particles, namely in space or when interacting with magnetic fields of various planets and stars. So this phenomenon does happen, and you can use this formula to figure out what the turning radius of the circular part of this helical shape is. But additionally, if we backtrack a little bit, the formula R equals mv over qb would be used to calculate this R right here, the turning radius of this circle. Similarly, within this picture, the R would be from here to here. And there will be an example or two of this on your upcoming homework as well. We'll take a look at a sample question for that. We have a proton moving at 1 meter per second. It's going to enter a magnetic field angled perpendicularly to its velocity. So we're going to use the same picture that I was describing for the mass spectrometer a second ago. Our initial entrance velocity is going to point this way. The magnetic field, in this particular case, since these are dots, or circles, representing the field vectors, these are going to point out of the page. Again, X's represent into the page vectors. It's, again, kind of like you're looking at the back feathered end of an arrow or at the hole in the paper an arrow made after it was fired into the page. So X means into the page. Dots, circles, mean out of the page. It's like you're seeing the tip of the arrow as it's coming through the paper, unfortunately, towards your face. So, this is our initial velocity vector, and the magnetic field points out of the page. If we use right-hand rules, Velocity points up, magnetic field points out of the page. That means our initial force vector is going to point to the right. This is consistent with what the drawing shows, because after the particle enters this magnetic field, it's moving forward, there's a force to the right, it's going to begin accelerating to the right, but as that velocity changes direction, the force will also change direction, and all the way throughout this particular circle, you will continue to have them in a perpendicular relationship, just like centripetal force. Note that the magnetic field doesn't change here. It doesn't have to. It remains perpendicular to both as this whole thing happens. So, proton enters at 1 meter per second. Since it's a proton, we already know what its mass and what its charge is. Mass and charge of a proton are considered to be known constants. If the orbital radius for the proton's movement is 5 centimeters, what is the strength of this particular magnetic field? So, a mass spectrometer has a constant field and then figures out what something's made of based on its turning radius. This is going to be kind of the inverse. Here we've already measured the turning radius, so we know what R is. And we're going to use all of our information, including R, to find B. We're going to calculate the strength of the magnetic field that is causing this to happen. So, our new formula, turning radius in a magnetic field equals particle mass times particle velocity, perpendicular to the field, divided by, I should specify, perpendicular velocity, divided by charge of the particle times the field strength of that magnetic field. We're told our turning radius is 5 centimeters, so that's 0.05 meters. Mass of a proton, again, you can consult the table from the chapter 15 notes. Mass of a proton is constant at 1.67 times 10 to the negative 27th. Our initial velocity is, and the number for the velocity will remain constant this whole time. All that's changing is the direction of the particle. The velocity number is 1 meter per second. Charge of a proton is also constant at 1.6 times 10 to the negative 19th. And what we're going to solve for is B, the strength of the magnetic field. So we know everything except B. We just want to get the B out from under here and send the 0.05 into the place it was occupying. And we should get a final answer of 2.09 times 10 to the negative 7th Tesla. Not a super strong magnetic field, but it's strong enough to do its job. It's able to deflect this proton pretty efficiently. 5 centimeter turning radius is pretty good. So, and again, B is magnetic field, T, Tesla, is the unit for magnetic field. Let me know if your math disagrees with mine. I didn't show every step of my algebra. I'm going to double check my work real fast. All right, I got the same answer as I did before. That's encouraging. So that is the B field that is causing this particular rotational pattern. Questions, comments, needs, concerns, please let me know. Now, this particular application of this phenomenon, the relationship between magnetic field and the force the field exerts on a charged particle, it has more applications than just this one. this particular application is a very useful one. As far as I'm aware, it's only really used in mass spectrometers, or that's the only example that I know of where it's utilized. But there are other places where this particular phenomenon does occur. Namely, in that this phenomenon, if a charged particle is moving through a magnetic field, that field can exert a force on that charged particle even if there's more than one particle moving through at a particular time. It doesn't matter how many particles there are, as long as a charged particle is moving through the particular object, there's going to be some amount of force. As a result, oh, that's a little odd. One sec, my graphics aren't the right size. All right. So, what is currently on screen is a demonstration of what happens when there's multiple charged particles moving through a magnetic field. And not even necessarily multiple charged particles on their own, like just flying separately. This is what happens when a magnetic field is exposed to a wire with electric current moving through it. In this particular image right here, this is a copper wire, and part of that wire is being exposed to a magnetic field. So these green X's represent that there is a magnetic field moving into the board, into the screen in this particular spot. And this wire, this copper wire, is currently being exposed to that magnetic field. Now, by itself, nothing weird should end up happening here. But something strange does start to happen if you run electric current through that wire. Notice, if you were to send current through this wire, then all of a sudden you have electrons moving through the wire. Charged particles moving through the wire, and that means that charged particles would be moving with some velocity through the magnetic field. As a result of that, if you expose a wire with current running through it to a magnetic field, and if the direction of current is perpendicular to the magnetic field, the field is going to exert a force on your wire. And in this particular case, this image shown right here, if the current is going upwards, so in this first image, there's just no current. I equals 0, no current going through this particular wire. In this second picture, current is moving vertically up the wire, so there is a flow of current. It's pointing in this direction. If we take our right-hand rules, current flow up, magnetic field into the board, that means that our force is going to point towards the left. The right-hand rules here and the force interaction works the same as if these protons weren't in a wire or if they were by themselves. And so, since the moving charges are inside the wire, the magnetic force ends up acting on the wire itself. And it literally would push the wire to the left, pushing it physically away from where it was. And if you were to invert the current, if you were to rearrange your circuit such that the current was flowing in a different direction, the force would point in the opposite direction as well. And again, if you take your right-hand rules, field into the board, current points down, force now points... this is an uncomfortable way to hold my arm. Force now points to the right. And so now, after changing the direction of current, the force will again point to the right now. What this means is this is one reason why magnets are bad for your electronics. You've probably been told in the past, don't hold a magnet up to your phone. Don't hold a magnet up to your computer. This is one reason why. Magnets can literally cause the wires inside of your device to get pushed around in ways that they aren't supposed to. If the magnetic field is pointing perpendicular to the current flow, that can push wires out into places they aren't supposed to go. That can cause some wires to be pushed into other wires that they're not supposed to touch. That can cause wires to sometimes just get ripped out of socket if they're not protected well enough or anchored down tightly enough. And so this is why, one reason why, magnets can ruin an electronic device. Holding a magnet up to anything computerized, like almost anything with just circuits in it. It doesn't even need to be computerized. You could probably ruin like your vacuum cleaner with a strong enough magnetic field. Certainly your microwave. Magnetic fields can destroy electronics for this particular reason. The fields will literally exert force on the wires as current moves through them. And so electricians, electrical engineers, anyone working in the fields of commercial electronics has to be aware of this when they are designing their machines. We'll talk about some additional reasons why later on, but for right now, note that if your machine needs to have a magnet in it for any reason, and frankly, most machines do have some small magnet in them to do some specific task. Like magnets are very useful. We use them a lot in motors and generators, and they have applications in circuits. And literally, if that magnet, like if you were building an electronic that needs to have both circuits and a magnet somewhere in it, you have to be very careful about how strong that magnet is and where it is in the machine compared to your circuit boards. So, magnetic fields can exert force on any moving charge, not just ones that are flying freely. It can exert force on current in wires as well. And there's a slightly modified version of the formula we've been using to describe that. Whereas before, it was F equals Q VB, and the V and the B needed to be perpendicular. Here it's force equals current perpendicular times magnetic field times length. And the length here is the length of wire inside of the magnetic field. So the L is physically how much wire is inside of the field presently as this process is going on. If you were to reduce the size of the field, then you'd get less interference. There'd be less length inside of the field if the field were physically not as big. And this formula is really the same as the previous one. It's the same information in both. Because if you think about it, electric current is defined as the flow of charge over time. So Q over T times B times L. So I is Q over T. Electric current is charge flow over time. So we can turn F equals IBL into QT times BL. Well, L divided by T is the same as velocity. That's just meters divided by seconds. So this formula is literally the same as the other one. It's just been rearranged in such a way that it has current in it to represent specifically the current inside of a wire, the length of the wire inside a certain strength of magnetic field. So it's not even really a brand new formula. It's the same as the one that we've been talking about all day. Questions, comments, needs, concerns, please let me know. We'll end today by looking at one more small example utilizing this new form of the formula. How much force will a half Tesla magnetic field exert on a wire with 0.0075 amps running through it? Assume 10 centimeters of wire runs through the zone of the magnetic field. So, in this specific case, L equals 10 centimeters. My handwriting is atrocious when I'm using a mouse. I apologize. L equals 10 centimeters. We know current. We know magnetic field strength. We can determine the amount of force pushing on this particular wire. So, our current is 0.0075 amps. Our magnetic field is half a Tesla. And 10 centimeters of wire is in the field, so that's going to be 0.1 meters. Multiply all those things together, and there's going to be 4.75 times 10 to the negative fourth newtons of force on this particular wire. Now, that's not a tremendous amount of force. You might feel that force twitch your arm hairs around, but it's not a huge amount of force. But this has the potential to get out of hand if, for example, there was more wire inside the field. Suddenly this force number starts going up. If the magnetic field gets stronger, this amount of force starts going up. If the current is any bigger, this amount of force starts going up. And as that force rises, you have the potential danger for more things going wrong inside of this machine. Because eventually that force is going to get strong enough to push things far enough and touch things they aren't supposed to, or possibly to rip things out of socket. And depending on what wires end up being crossed, that can kill your machine. So, magnets, don't put magnets anywhere near your commercial electronics. But you hopefully already knew that. That's where we'll end it today. We've talked about a few varied applications of this phenomenon already. Again, any questions, needs, concerns, please let me know now, or I'll also be here as I usually am for the next hour or so if you jump back in with questions. So we'll call our break here for today. Do be going over this information, looking over your homework. I encourage you to, as always, start the homework as soon as possible. I'll be here for the next hour if you have questions. Tomorrow we will go over more related examples and cases, sort of further talking about why this phenomenon can be a problem, in addition to the good things it does, like mass spectrometry and also keeping Earth safe from the sun. And stay tuned for what I say about labs, because I'm still planning things. Details are a little bit fluid, but I will let you know by tomorrow what we're doing for lab this week. And I'll let you know by Thursday I am stumbling over my words like crazy. I am sorry. Check your emails. Let me know what questions you have. And if I don't see you again today, I will see you tomorrow.